Thank you for sticking around. This really complements well for talk because I'm going to be talking about orange glass beads as well and trying to understand the conditions of the eruption. This is work from a group of us at Brown, some great analysts at Harvard, the Center for Nanoscale Science, over there, and Ryan, who helped us with some nanosims analysis. And this is under the Lunoscope serving. And just to introduce the beads, here's an orange glass bead. Actually, it's probably a black glass bead from 74001. This is a 10 micron scale. And you can see it almost looks like a planet at this scale. There's so many features on it. You could really spend almost a whole thesis on a single bead. There's so much information here. And if you haven't seen a fib pit, this is what you can do with these focused ion beam machines. You can cut out a little 10 micron chip of this and go to town on it analytically, which is what I set my graduate student, Tom. Tom just published this paper this year, and he really threw the kitchen sink at these beads. And what I want to show mostly today is his work looking at the surfaces of volcanic beads, but hopefully get you to the end and convince you that this would be a good thing to try to do on impact glass. All right, and so it's kind of the same framework that we have with pyroclastic eruption. And I just want to point out that as you have different trajectories, you can have beads that experience different pressure temperature paths through the gas cloud, but land at the same place, right? And so this is how one way we can get a mix of orange and black beads at the same deposit. We can also imagine it as this eruption waxes and wanes. You can get a stratigraphy of different conditions. And these are the kind of things we want to do. Ideally, we want to trace out different paths of beads. And if we can get statistics on them, you can say something about the eruption. And the amount of information you can get from the beads is incredible. So Alberto Saul and Eric Howry and others have looked at the initial stages when the bead comes right out of the throat of the volcano, maybe even in the conduit. Temperatures are high. The vapor pressures of volatiles in the bead are higher than the external pressures. And so you have diffusion outward. And so here's water, chlorine versus distance. The core of the bead is here. And we have diffusion out profiles. So this thing is diffusing gas out. And this is what Alberto used to infer high water contents in the bead originally. But in the last few years, there's been some really great work from Yoshua Zhang and Su and others looking at diffusion in. And this is maybe a little less well known, but it's fantastic. As the bead cools, the partial pressures of some of the volatiles in the bead decrease, and they can actually decrease below the external pressure. And so then you get ingassing, and the evidence for this is if you look near the edges of the beads, and here's sodium in a couple of different orange glass beads, you actually get higher concentrations, and this is showing diffusion into the bead at a later stage. This is in this kind of intermediate step 2. And then finally, as the bead cools, the gas becomes so cool that you actually precipitate solids out of it. And going from solid to gas is sublimation, so going from gas to solid is desublimation. Often these are called sublimates or condensate on the glass beads. And in atom probe tomography, they look like this. So if you're not familiar with atom probe tomography, we're imaging individual atoms in 3 dimensions, and you can image tens to hundreds of millions of atoms and reconstruct where they were and what they were using time of flight mass spectrometry. So here's the glass, and here's the surface coating, and again, here's a 100 nanometer scale bar. So this is from Tom's paper. This is, again, a black glass bead from 7401. These are mounds, zinc sulfide mounds on top of the glass. These things had been seen in the 70s when the samples were first returned, but at that time the SEM and the tools we have, the technology is not nearly as good. And now we can see a whole larger array of phases sitting on the surface. Oh, I should go back. Yeah. Yeah, Liu and Ma are doing fantastic work looking at the surface of the beads as well. We're not the only one working on it. And so there's a whole array of phases that Ma and Liu and us have found on the surface. Some of them we've identified, some of them not. And there's a stratigraphy to it. So at this like nanometer scale, these coatings are 100 nanometers thick at best. You can actually see a sequence of deposition. Do that fib lift out, get a TEM little chip. This is 50 nanometers. And the advances in technology and be able to getting analytical data at this scale. Here's the silicon oxygen from the glass bead. Here's sulfur and zinc sitting on top of it. And here, notice this little iron layer sitting in between the glass and the zinc and sulfur. We can confirm this with atom probes. So here's magnesium, here's zinc. So that's the glass. This is the zinc sulfide. We can do kind of virtual profiles through here. So this is nanometers. This is the glass. This is the sulfide. This is zinc. And notice this little red thing, that's the iron, that little iron layer. And you can't see the numbers, but it's 6 nanometers thick. What can we do with this information? Well, Tom did some great thermodynamic modeling, temperature versus pressure, gas pressure in the cloud. This is the path of a bead, an isentropic path. This is the glass transition. And he's showing here, the models are showing that iron sulfide is stable at high temperatures, and zinc sulfide becomes stable as it cools. So as the bead cools, the first sulfide we'd expect would be iron rich and would go to zinc rich, and that's exactly what we're seeing here. And so we can extract pressure temperature conditions from the nanometer scale. And this is just one of them. You can try different things and try and get different pressure temperature points along the path from this nanometer stratigraphy. And so what we want to do is basically port this over to impact. Why would we want to do that? Well, in some very gross comparison, an impact has some similarities to a volcanic eruption. There's a high temperature origin. There's a gas cloud produced with melt blebs in them. And so a lot of the same processes should occur. The target rocks will probably have a lot less volatiles in them than the volcano. And so you will expect less volatiles in the bead. They might have a much higher temperature beginning. So there might be more outgassing.
2 minutes.
Fact, when we look at impact, we have one more slide. When we look at impact beads, they are very devolatilized of water and other volatiles, but there are other moderately volatile elements and slower diffusing elements that we hope to see diffusion profiles in. So we're going to go hunting for that. And so, yeah, the goal of the next couple years, the Apollo samples, the soil samples, I just got the message that they arrived at Brown, and one of my grad students is going to pick beads, impact beads out of these, and we're going to kind of do all 3 of these things. We're going to look for diffusion out from the early processes, maybe some diffusion in if we can find it, and then there are desublimation phases on the surface, not nearly as much as is on the volcanic beads, but there's a little bit there. So we're going to see how much we can extract from them. And then the goal would be if we can get enough PT, XT information, we can maybe connect these to potential source craters. You know, say there's a big crater, must have a higher temperature pressure condition. And a little bit, there's this also lingering thing of distinguishing impact beads from volcanic beads. And if we understand what impact beads look like, we may add to this ability to distinguish volcanic and impact beads.
Our final speaker for this session is Anthony Gargano, talking about mass balance considerations for redox state disequilibria during explosive volcanism on the moon.
I think that works. All right, great. Hey, everyone. Thanks for staying to the last talk today. My name is Tony Gargano. I'm a postdoc at the LPI and NASA JSC. And Thanks, Steve, for setting me up really well for the background here. It makes my life much easier. So this is some conceptual work that Aaron Bell and I have been working on for the past few months, and it's just now starting up, as well as my collaborators at NASA JSC. And here we're considering how the electronic mass balance should be considered in terms of how outgassing and ingassing behaves in lunar pyroclastic glasses, but this is also applicable to many other scenarios as well. So that works. Awesome. All right, so like I said, Steve set us up really well here for how the system works here. Now, I used to think, and I still kind of think, that these lunar pyroclastic glasses are some of the most extensively degassed materials on the moon. And it's because the conditions they erupt in. These things erupt very hot, and within the volcanic conduit, we need to have these high gas to melt ratios just to fragment these materials and exhume them as well. So we have this system of high melt eruption temperatures. These things have a lot of gas around them, and importantly, they have a large change in pressure during their exhumation and cooling path in the plume. And this kind of tends towards the idea of these things being extremely degassed. Now, on the image on the bottom left here, I'm showing you the orange and black glasses. In this work, we're looking specifically at the black glasses here. Their initial melt comps are probably very similar to the orange glasses. Simply, their cooling path is much more slow, meaning they crystallize in the plume. And we're going to exploit that behavior in our work here to understand whether or not the redox conditions are changing as these beads cool and in and out gas in the plume. All right, so ironically enough, I think the gassing processes are best understood here in terms of sulfur isotopes. This is a plot on the bottom right showing you some lunar volcanic materials where we're showing the sulfur isotope fractionation as a function of sulfur loss. And specifically in the case of these pyroclastic glasses here, these seem to be the most degassed materials, but importantly, they're degassing under equilibrium conditions, meaning that they're maintaining their equilibrium vapor pressures throughout their loss of sulfur and cooling. But this process is not unidirectional, as Steve just mentioned here. The outgassing process is also buffered by some amount of ingassing as well. So evidently, we have some amount of buffering that's occurring during this devolatilization process. So really, my goals here are to better understand the overarching controls for elemental volatility and whether redox influences how volatiles are lost or gained, and specifically the kinetics of how this rate changes during this condition. So we're looking at the black glasses again as a conceptual idea to test this idea. And really what I convey here is that in terms of how outgassing behaves here, if we look at the simply sulfur degassing equilibria here, we can see how FO2 influences the efficiency of this degassing process here. The plot on the right is showing you the same system here, where a high FeO-bearing melt, the equilibrium vapor pressure of sulfur is a function of both the FO2 and the sulfur content here. I think this behavior, this Hindrian behavior, where the volatility is proportional to the concentration, is not considered very much. But in this system here, where these glasses are losing sulfur, potentially being reduced, we're basically tending towards equilibrium constantly as we're going towards lower FO2 and losing sulfur contents. Let's see here. So yeah, I think these two processes together in terms of the loss of volatiles and the redox state changes tend towards explaining why many degassing materials tend towards equilibrium, even though they're losing a lot of volatiles. All right, so in terms of how we're conceptualizing this, we're saying a simple electronic mass balance of a orange glass composition as it loses volatiles. So in this case here, I'm comparing and contrasting how sulfur and sodium are contrasting in this way. So if you compare simply the redox reaction of how you lose volatiles from the species in the melt, for sulfur, it's dissolved with sulfide. For sodium, it's an oxide. So we need to oxidize our sulfide to sulfur in order to lose it as a gas phase, and conversely for sodium in this case. So we can see here that the electronic mass balance can be maintained if these things are lost together here, but this must be balanced in some way. All right, so what we're doing here is that we're using polyvalent liquid trace elements as a first order test whether or not this matters at all, or if this process occurs. So in this case, looking at vanadium, chrome, and titanium here, we're going to begin with vanadium here because vanadium its partitioning behavior is very sensitive to redox state. So on the left here, I'm showing you how the vanadium olivine melt KD changes as a function of FO2 here. And on the right, we're showing you an image of these black glasses here. And simply speaking here, we'd expect to see a change in the vanadium partitioning and the olivine as a function of the redox state, as if these glass beads do in fact change redox state or are buffered the entire time. So as Steve mentioned earlier here, these materials are kind of a natural Monte Carlo simulation. They experience different trajectories, different paths. So we expect to see a large variation here depending upon what occurs, but really we're going to exploit this behavior first and foremost to see if it matters here. And likewise, you'll see how the KD changes as whether or not reduction or oxidation controls drives the bus here. All right. And really, my main interest here in tying this together in terms of both the moon and also the early solar system too is understanding are volatile elements operating the buffer melt redox state. Many volatile elements have high diffusion rates. So in terms of buffering redox state, these make the most sense in terms of making sure things are balanced the entire time. So in terms of understanding both how melt is buffered, we need to consider how loss at in-gassing behaves and which one is controlling the system here. And ultimately, this also tells us towards the chemical kinetics of the rate of loss. And this is the necessary information to interpret some of the volatile element stabilized state data being generated these days. All right, so stay tuned for updates. We're starting on this work doing some SIMS analyses of vanadium pretty soon here. And look forward to sharing it at LPSC next year. And please reach out if you have any questions and look forward to questions.
All right, we're going to start the panel discussion, the Q&A. So we're going to ask all of the speakers to come back to the stage. I'd also like to thank all of the speakers for staying on time. So we'll have the full 20 minutes for the panel discussion. For in-room participants, if you have questions, please line up at the mic. Any virtual participation or virtual participants, if you have questions, just put them in the chat, and we are monitoring that up here.
Sorry, I guess sorry. Yeah, thank you for all the great presentations. My first question is for Lingzi. So it's interesting the Gersite distribution you are trying to locate and trying to pinpoint. I wonder how that relates to hematite finding on the moon. The reason I'm asking is if we do have Gersite, if there were impact gardening, do you expect any correlation between that and the hematite finding on the moon? This is left field question. So, yeah, thank you.
Yeah. So Schweiz's hematite distribution is basically the same pattern, concentrating toward the polar region and the near side of the moon. So they're definitely correlated. And Schweiz's theory was hematite was dehydrated goethite.
Oh,
so
okay.
they're definitely correlated.
Thanks.
Hi, Paul Lucy, Marriott Hotels. Ed, that's great work, really interesting. I just wanted to mention that, you know, the PSRs in general are unique, not well, unique, but different from the background in both the Lyman alpha and at the laser wavelength. And those, they kind of shied away from the ice explanation, more sort of differences in physical processes. So could the physical state, constant low temperatures, be affecting, say, gardening or something to cause this radar distinction between the PSRs and the background?
Yeah, so although the PSRs look different for other wavelengths, we have not seen a difference in their radar properties. And one of the reasons that I am cautious to saying, hey, I found a signature of water ice, is we need to do a little bit more analysis to actually be able to untangle the effect, because dielectric permittivity can be changed because it has water ice, or it could be changed because it's fluffy or regolith, or less fluffy regolith. So we need to do a little bit more. That way I could actually tell you yes, water ice, or no. Yeah, thanks for the question.
Hi, I'm Sarah from Georgia Tech. I had a question for Charles. Sorry.
Carl. Yeah.
So were there any measurements taken after the ice deposition for when you had the ice putting? Yeah.
So the way we did experiments. When it was in the glove box, we would do intimate ice mixed in with the regolith, and we'd make the measurements. And glove box went out to 2.5 microns, right? Now, when we did the measurements in the vacuum chamber, we either did the same thing, or we, wetted it and ground it all up. And then when we put it in the vacuum chamber, we found that the surface already desiccated, and so then we lazed it to break it apart and got the fresh surface exposed. And then after that, we open up the chamber and let Maryland air get in to form the frost. So that was procedures. Did that answer your question?
Yeah, that actually
Okay.
did.
Great.
We're going to interrupt the in-room questions for an online question from Janice Bishop. Feel free to unmute, and this is for Ling Zhe.
Hi, Ling Zhe. I was really intrigued by your talk, and I think you've done a great job mapping this intriguing feature at 1.5. However, I don't think this could be goethite because I've studied the spectral properties of iron oxides for over 30 years, and goethite doesn't have a band at 1.5 microns. So I suggest you take a look at the Relab database and look at goethite spectra there. And I don't know why the USGS spectrum of goethite that you showed has a weird band at 1.5, but they have Roger Clark and Greg Swayze published a paper in 1990 where they identified scapolite on Mars, and then they had to retract it because of an admixture, an anomaly in one of their lab spectra. So I would proceed with caution, and I think you've done an excellent job with your study, but I suggest you go back and look more carefully at goethite spectra in the laboratory. And I'm guessing you found some really interesting kind of ice, different from the normal ice, or maybe something else. Minerals don't typically have a band at 1.5, so there are some wacky, weird ones that do. So maybe you found that, or maybe it's some intriguing new kind of ice that that is novel and interesting too. So I think it's a great discovery, but I don't think it's goethite, and I want to save you from the mistake that Roger Clark and Greg Swayze made in 1990.
Yeah, thanks for the comment. We found several other literatures that showed goethite have this 1.5 micron absorption, which is the OH. That's a typical OH absorption.
Yeah, OH absorptions usually occur at about 1.41 to 1.45 microns, and in constrained environments, they can have a band up to 1.47, like in academia, but I would be very cautious with this interpretation.
Okay, thank you.
Okay, so my second question is for Anthony. In Su et al. 2025, we looked at the sulfur ingassing into the orange beads, and I think we stopped at talking too much about the sulfur outgassing and ingassing because of the valence consideration. So I probably missed the point that when you talk about the modeling, like sodium outgassing has to be oxidation or reduction related, and the sulfur is more like oxidation involved. So I was wondering whether it's just my misunderstanding, or you're actually looking at more combined, because we do see both happening in terms of outgassing of both elements, ingassing of both elements. They may be separated somehow. The ingassing thickness is different. In addition to that, when the sodium outgas, they recondense as sulfide. So there is a very complex story here. So I'm just kind of wondering, when you do the modeling, what are you planning to do?
Yeah, so I modeled it as simply loss first to indicate the directions, to indicate that the reverse is the opposite. So I guess what I would say is that the electronic mass balance, if both things are ingassing, the redox state must be changing. It must be. There's no other answer for that. So until that data showed the sulfur ingassing too, I was like, oh, that's curious. If we accept both are ingassing, we must have a redox state change. So yes, it is very complicated, and I think I've settled on what I think is the most. If this is real, this should show up to see if that matters. But in terms of the modeling, I'm not quite sure yet. It might be equilibrating with the plume the entire time, to where that's what it is. But we should talk more about it because I doubt I have the right answer completely.
Okay. Yeah. Thank you.
Jeff Gillis Davis from WashU. My question is for Pratik. I was curious, in your model, does viscosity of the melt and the composition of the volatile that forms the bubble play a part in how quickly the bubbles coalesce? And can you infer anything about the composition of the volatile that made the bubble from those modeling? Excellent talk, by the way, too.
Thank you. So like I have just shown the equation in the presentation, but we are using a differentiation form of it. And like at every step, we are changing the viscosity. Like we are calculating the viscosity from the liquid S temperature to the glass transient temperature. And at each time step, we are integrating the viscosity, like how it is changing with time. So yeah, so we are changing the viscosity, and we have seen that like beyond like 1150 Kelvin and lower, the viscosity becomes too high, like for bubbles to coalesce or relax its film. Like if it's relaxed, it's maybe few microns. Like coalescence cannot take place beyond that temperature because viscosity is becoming too high. When some literature say that at that temperature, like olivines also start to crystallize, and that can also increase the viscosity. But regarding the composition of the vesicles, we are not sure what those compositions are because we don't have the entire glass bead. We just have a cross section of them. So during procedure, like they are expected to like loss of volatile from the which was trapped within the bead. So I don't have any comments on the composition of the vesicles, but we expect those are mainly sulfur or maybe dissolved H2O because there are some studies on these orange glass beads to understand the liquid like volatile content from the origin of the melt, and they has like mainly sulfur and H2O or OH.
So you can't simply assume a load or pressure outside the bubble and the composition inside the bubble of a volatile and the expansion rate of the different molecule and give you the size of the bubble for kind of a inside outside pressure.
Okay, I will look into that. Even like we are also like if a bead is cooling in a 1 second, we also expect the bubble might grow in that period of time. So we'll also integrate the bubble growth model into that and see how it is affecting the time scale as well. Thank you.
I'm going to jump in with a question that's in the chat online here. This is from Ardith Bravenik for Lee Ciao. Do you have a sense of the minimum millimeter required to protect the amino acids?
That depends on the duration of irradiation we're talking about. So for the study that we did do, 8 millimeters had a survivability rate of at least 90% for the equivalent of about 2.5 years on the lunar surface. So that's multiple variables happening at once. That gives you a sense of what's needed.
This is Paul Lucy for Carl. So I totally agree. 3 microns is a great place to look for water ice, but a technical challenge is there's not a lot of light at 3 microns in the PSR. It's just the way the sun and thermal interact. But I did want to make the comment that ice has a really strong 12 micron band where there's a lot of light in PSR. It's just a comment and maybe encourage you to take a look at that in the lab, or we could work together on it.
Let's work together on that. My system stops at 8 microns. Okay, sounds great synergy.
Thanks, Sarah Soul from Georgia Tech. I have a question for Janice, more of a clarification. Unfortunately, 10 minutes is just not enough time to go through as much explanation as you would like, but could you repeat what you mean by you coming up with different forms of hydration?
Sure. What we see is a different shape in the band depth, the band parameter near the hydration band near 2.7 to 3 microns. And for the highlands, we see sort of a plateau or a bowl-shaped change in the water from morning to midday. And for the mare, we see increasing shape. So we see when we're mapping this hydration band across the moon, we see changes in composition and changes with time of day, which has been seen before, but we looked at this more carefully in terms of specific regions of the moon. And now it really seems that there's a persistent hydration band that's present in some materials. And then there's a variable hydration band that's present in other materials. So in the mare, there's this variable component with time of day. And in the highlands, there's a more persistent component that doesn't seem to change or changes less. And so it really looks like there are two components. Does that answer the question?
Yes, thank you.
I'll jump in with another question from the chat. So this is from Janice Bishop for Zi Huang. I think your work is very important to understand the M-cube hydration bands. I'm wondering if you have tested different types of mineral structures in your modeling.
Yes, so this is definitely our next step. So we're planning on doing this for olivine and also ilmenite, especially for those complex, and also like for complex mineral structures compositions. We're hoping to test. I think there's a recent paper identify like different variation of 3 micron bands depending on different mineral species. So this is what we're planning to do so as well. Thank you.
Hi, this is Paul Sabo, UC Berkeley. I also have a question for CU. Maybe I missed it. Is there a big difference whether you have a silicon or an oxygen point defect in the simulation?
Yeah, so there's definitely a very huge difference. Unfortunately, given the time limit, I don't have the time to show all of them. But essentially, like silicon defect is going to trap those hydrogen very effectively, and also the oxygen defect is going to trap the water more effectively. And also, there's also an interesting deviation for the spectra, given the trapping of water with silicon oxygen defects. I'm going to show that in the full paper, so you can check it out.
Thank you.
Paul Lucy, this is for Janice. Janice, I noticed in your diurnal plots that there was pretty weak latitude dependence, but Schweile's maps show a really strong latitude dependence. Can you comment on that?
That could be due to the thermal correction that's used. And Roger Clark came up with an initial one at the time the M-Cube team was working on this, and then that was improved by Schweile and Josh Banfield and also Christian Vuller, and then his grad student Kai Wolforth used data from the Galfun mission and from Diviner, and I think his thermal modeling makes the most sense from physics, and it's what's used by the asteroid community and others. So I think Schweile's method is also reasonable, and I don't know why the magnitude is different, but it could be that there's some variations in maybe he's detecting more because of how his thermal modeling is correcting the data. That could be.
Okay.
But I think that the trends are pretty similar to what Schwei's finding and what we're finding. It's just a matter of magnitude, whereas the early corrections that Roger Clark did were a little bit different character.
Yeah, and Josh Banfield, his correction showed very little latitude dependence too, though he didn't look at the diurnal. So I guess there's still more work on the thermal correction to get a consensus.
Another question from the chat, also for Janice. It is, where do you see an increase in OH and H2O with an increase in pyroxenes and also with lunar diurnal cycle? And how are you considering the thermal emission effect around 3 micron band? And what calibrations are you using?
Okay, I did answer that in the chat, and we're using the thermal calibration from Christian Vuller and Kai Wolforth, and they corrected this with the Diviner data as Schweile did, but they also used the Chinese Galfun mission in order to characterize the thermal. and ensure that it's consistent with physics. So I think their thermal correction is the most accurate, I believe, based on physical properties and remote sensing of airless bodies. And the pyroxene, I think that's not something new here. Pyroxene's known to be more consistent with the mare, and we're just kind of pulling this together in this talk. So looking at the lab spectra and looking at the change in shape of the hydration band from morning to midday is what we're looking at here. I don't know if that addresses the question.
This is Caleb Fassett from APL. I have a question for Pratik. This is probably a little ignorant, but you showed this really interesting trend in the core of the orange glass beads at the top and the black at the bottom. But I guess my question is, like, what fraction of the core is glass beads going from the top to the bottom? Is it like radically reduced as you go from the top to the bottom, or is it sort of a constant amount through the core?
So if I understood correctly, like how much is glass at the top and black at the bottom?
No, you gave the sort of the what the different types of beads were, but how many beads are there at the top and the bottom is the question I have. Is it sort of homogeneous, or is it decreasing with depth? Or
yeah, like more or less, like in the smaller fraction, the amount of glass is much more. Like, but if I go for a pyroclastic bead size for 250 micron and above, black, the crystalline becomes more dominant because there are no glass beyond 500 micron. Like I'm getting black beads, and this is consistent across all the depths. So, but for smaller fraction size, the glass remains around 20 to 30% at the top of the drill core, but at the bottom it's less than 10%.
I have a question for Steve. I think this is a cool idea of using the glass beads as analogs for thinking about impact glasses, and I've just been sitting here sort of pondering how the differences in the initial condition would affect the chemical profiles that might develop. Like the temperatures would be so much higher.
Yeah. So people have looked at impact glass beads, and partly they distinguish them from volcanic beads by the basic absence of water and other vols. So they are highly degassed, and the assumption is that they had a much higher temperature origin. And so then we're thinking of looking at like copper or zinc and see how, and moderately volatile elements that may be preserved even in this high temperature regime, for sure.
Yeah, this is for you. So I'm a little concerned about the net intensity of the infrared absorption imposed by your process. So I guess my question is, for a given hydrogen atom, how long does it persist as in the form of hydroxyl versus not hydroxyl? So just an estimate. You said that the lifetime of the bond is very short. So if it's usually hydrogen, then the net absorption is going to be fairly low. So, but can you comment on the lifetime as hydroxyl versus lifetime as hydrogen?
Life as hydrogen, you mean atomic hydrogens or?
Well, for a given hydrogen that sometimes is bonded and forms a hydroxyl that's long enough to form an infrared absorption, is it 99% of the time hydrogen, and once in a while it's in hydroxyl, or is the hopping so frequent that it persists as hydroxyl for a long fraction of its lifetime before it diffuses out?
See, so, yeah, thanks for the question. So essentially, right now, based on our current simulation results, we only see like transit hydroxyl form with different oxygen. So I wouldn't see that as a consistent hydroxyl oxidation, because again, the lifetime is now as long as 1 picosecond, which is the lifetime for hydroxyl stretching. So I wouldn't see this as honestly, I don't think this is also like free hydrogen, because I would consider free hydrogen as diffusion among the interstitial silica surface and also within the silica. So I would say like right now, we're going to do more simulations and also identify the lifetime for like individual hydrogens and also the lifetime for this hydroxyl. But right now, at least limited to this defect case, we are seeing like transit hydroxyl and now, and and they're like very, very short term, less than 1 picosecond.
Tom Orlando from Georgia Tech. This is for Ardith. The question is related to the. So you showed some really nice glass transitions and phase diagrams, but this is an assumption that these things are in thermodynamic equilibrium. But when you look at the cryovolcanism, there's this very, very fast thermal extraction rate. So it's the cooling rate that really matters. You can get in an argument if you have a really rapid cooling, you're not even thermodynamically coupled through the metal stable state through supercooled water to the glass transition. So there's a lot that has to do with the sort of overall cooling rate. So could you sort of address that as how that would fit into your sort of modeling and your overall picture of these complex solutions?
Yes, thank you so much for the question. I actually had another slide that I entirely deleted that had to do with the critical rate and cooling rates. But I will back up a little bit and say that the reason for this project was that here in Curation, when we were trying to synthesize some icy simulants to do some cryogenic regolith ice testing, one of the problems was that depending on the cooling rate, depending on how we were doing vapor deposition or trying to dose the regolith, we were often observing glasses instead of crystalline ices. So no, the critical cooling rates for many of these in the literature review haven't been reported. There's not a lot of data there at all. I think there needs to be a lot of experimental work to really fill in those gaps because, as you say, that's another entirely important part of this picture. But since we have experimentally observed some of it, I do think that they are going to form glasses.
Yeah, all right, thank you.
And we hate to cut off the conversations here, but it is 11 o'clock, so the session is officially over. We encourage you to chat with the speakers during the break or email them if you have any more questions. And with that, let's thank the speakers again.
Have you ever seen these ilmenites? And like and they sit like you can see the sublimate, but sometimes you see sublimate on top of ilmenite. Lower energy barrier for condensation. There's nuclear, but also redox, right? And yeah. So I wonder if iron. Well, I don't know. Maybe I missed it in the talk. I think you were just looking at sodium and sulfur. Yeah. I think, and this, I don't know if you've ever read any that iron gets involved. When he saw these, I think he was talking about these ilmenites nuclei on the surface of the redox. And so I wonder if that is part of it.
I should look into it. I mean, part of it is that Aaron and I are working on what sulfur operates first. Like, what is the kinetic limitation?
Yeah,
I think it's sodium because it's just fusion so much faster. But iron should be driving bus,
but I would look. I think what Reed would talk. Yeah. And he's retired. He's a little hard to get hold of. He's great to talk to. Look at the surface. See what phases are good. He did these like really producing experiments on like levitated beads, and he got all sorts of things to precipitate on the surface as whole vacancies are diffusing in it. Yeah. So it sounds like this is stuff you're thinking about. But I think iron. Yes, iron. He would say think about iron, titanium, other things that sustain balance and balance some of those.
Yeah. No, I should get into more the surface. No.
What's the thing? Yeah. I know. Is that like an official, or is that? Oh, yeah. Yeah.
That sounds great.
Thank you.
Good morning, everyone. I presume that all the parallels are done, and we're not. I know a number of people had to go to the airport, kind of the usual NESF thing, right? So I'm really glad that all of you are still here, and just to share something, Christina and I always talk, and Brian, we always talk about dividing up the awards. And this year I usually do Shoemaker and Yvonne before me and Dave Morrison before me. But I decided this year that I wanted to do Niebuhr because of the young people, because of the future, which, I'm going to talk about in my last talk of the day. And it's you guys are where it's at. You guys are going to be taking the reins, as I was telling someone a little bit ago. Whenever I see some usually old white guy complain about the next generation, I say BS. I know them, and they're fabulous. And so, speaking of fabulous, this is the time to announce the Susan Mahan Niebuhr Early Career Awards. I believe I met Susan just briefly many years ago. She passed way too early from cancer a number of years ago. Her husband, Kurt Niebuhr, you may know, is senior leadership at PSD, and he gave us permission to name this award after her. And she was passionate about the next generation. And so we figured, we need an early career award for all of you guys that are doing just jaw-droppingly amazing stuff, and naming it after her just made so much sense. So this has been going a number of years. I don't remember how many, but I think at least 10. So I want to announce the 3 winners. One of them couldn't be here due to a personal crisis that's going on, but gave me some paragraphs to read. But 2 of them are here, so I'll read all of their names, and then I'll start with the first one. So Ariel Deutsch, Tab Prissel, and Jacob Richardson. So let's give them all a hand. So I'll talk about Ariel first, since unfortunately she can't be here. Ariel Deutsch, Dr. Ariel Deutsch, is a planetary scientist whose research spans the Moon, Mercury, Mars, and Earth. She's recognized for her groundbreaking work on surface processes and volatile dynamics on airless planetary bodies. With a deep background in geology, remote sensing, and statistical modeling, Dr. Deutsch has authored over 35 peer-reviewed papers. Not bad for early career, right? 17 of them as first author. Her research has advanced our understanding of lunar volatiles through innovative analyses of terrain roughness, crater ages, and the distribution of ice and ejecta deposits. Ariel is a key member of multiple NASA and ESA mission science teams, including Artemis II, Viper, and Lumio, and she's the science lead for NASA's Lumen project, which develops new techniques to map permanently shadowed regions on the moon. Dr. Deutsch has also made lasting contributions to community leadership and education. She's served on the Mercury Exploration Analysis Group Steering Committee, organized major science meetings, and mentored students in Washington, D.C. and Puerto Rico. Her scientific achievements, leadership, and outreach embody the spirit of this award, and so we join in congratulating her, and we wish very much, and I know she has expressed to me her wishes that she could have been here. But at this point, let me read what she sent for me to read and her acceptance. So these are her words. I'm very grateful to be receiving the Susan Mahan Niebuhr Early Career Award, and sharing this recognition alongside Jacob and Tab is all the more meaningful. I've had the pleasure of working with and learning from Jacob over the last few years on NASA's Jet 5 and Artemis II teams, and he always inspires me to push boundaries and have fun as we have the privilege in shaping crewed missions. While I haven't had the opportunity to work with Tab yet, I've long admired his interdisciplinary approach and the way he brings the spirit of geologists are storytellers to his work. I hope we have the chance to work together one day. Unfortunately, I never had the honor of knowing Dr. Niebuhr. It's been very inspirational reading about her dedication to promoting early career researchers and women in planetary science. That's something I neglected to mention at the beginning. She was a big advocate of that. I hope that I can continue to welcome young researchers and women into the field, just as Dr. Niebuhr did for so many others, and just as so many mentors have done for me. Listing the team of mentors who have helped me reach this point in my career would probably entail listing half the people in the room. But I would like to thank a few key people who have been instrumental in my development. This includes Nancy Chabot for 3 years of mentorship during my undergraduate summers at APL, and for modeling alongside Brett, Dave, Carolyn, Noam, and Rachel how fun, interesting, and challenging the field of planetary exploration really is. Of course, my PhD advisor, Jim Haddett Brown, for challenging me to push myself and always supporting me in achieving my dreams, and his continued guidance and friendship to this day. I'm very grateful for my time at Brown and learning from others, including Carly, Pete, Schwei, Ralph, Jack, Alex, and Brandon. Also, Greg Newman, my graduate fellowship advisor at NASA Goddard, for developing my technical skills and appreciating curiosity in all corners of the solar system. And finally, my postdoc mentors, postdoc advisors, Jen Heldman and Tony Colaprete, for their guidance and unwavering support, and for continuing to share in new opportunities with me. With this last paragraph, I want to thank Greg and Christina for leading an institution that values mentorship and community support. I'm grateful to have found a career that doesn't feel like work. Do any of us feel like this is work? And to be surrounded by people that excite and inspire me. I hope I can always find avenues to share my interests in planetary exploration with others in a meaningful way. I'm thankful for Survey Resource for supporting my advising of high school students as part of NASA's GLEE program, and for growing my mentoring skills by supporting me in NASA's Planetary Reach program, engaging local youth with NASA science and exploration in Puerto Rico. I was really disappointed to hear that NASA terminated Planetary Reach, and I encourage everyone to continue to find ways to collaborate with your local communities in your amazing work. We have the coolest job in the world, and sharing even a tiny piece of it with others can make a meaningful impact. So Ariel, you'll watch this video, I'm sure. Congratulations from all of us. So I'd like to share a few words about Tab next. And Tab, you are here, right? There you are. All the way over there. So Dr. Tab Prissel is an assistant professor at Purdue University, where he studies the igneous evolution of the moon and other rocky planets. An experimental petrologist by training, Tab has made major contributions to our understanding of lunar magnesium sweet magmatism through his analyses of Apollo samples and lunar meteorites. His work integrates lab-based experiments with orbital data and geochemical models, shedding light on the moon's early magmatic history. Before joining Purdue, Dr. Prissel was a NASA civil servant and research scientist at Johnson Space Center. His commitment to community service is equally distinguished. He serves as the Workforce Development Chair for the Lunar Exploration Analysis Group and as liaison to the Next Generation Lunar Scientists and Engineers Group that we heard Jake talk about, ensuring that early career scientists have strong representation and mentorship opportunities within the field. As vice chair of the League Science Goals theme on lunar origin and early history, Tab has led collaborative efforts to establish research priorities for NASA's Planetary Science Division. His leadership, scientific excellence, and dedication to inclusivity make him a truly deserving recipient. So please help me congratulate Dr. Tab Prissel. Yeah, and here's the award. And Christina, would you like to come up here too? We can get a picture of the three of us, and then Tab will give his acceptance. Okay. All right. Thank you. Congratulations. My pleasure. Absolutely. Okay. Okay. Thank you very much to Greg and Christina Servi, the awards committee, for considering me. As Ariel mentioned, looking at my fellow recipients and then the previous awardees of the Niebuhr Award, I feel immensely honored to be among that list and join them with Jake and Ariel. Also to have my name recognized with Susan Niebuhr and her contributions to the field and also to the development of our workforce is also a huge honor for me. I was asked, I didn't know, what to really present on. And they said, why don't you talk about, how you got into science? And that's a little bit of the story. I guess another part of the story that I decided to share today will be how I guess, stayed in science. But first, I want to recognize two advisors, my academic advisors, and Russ Colson. I didn't like science growing up, truthfully. I thought I went to school for graphic design or music industry. And I took a historical geology class with Russ at Minnesota State University Moorhead. And Russ is the one who told us that geologists are storytellers. And actually, he first jumped up onto the table in the front of the classroom and pretended with all of his heart to be a velociraptor. But then he told us geologists are storytellers. It was a gripping moment, so we were listening. But with my interest in art and music, and especially as these soulful forms of communication, the storytelling of geoscience immediately resonated with me. And so that was the first time I opened myself up to learning how to read and tell the stories of the earth, sky, and planets. And so I wouldn't be here without Russ. And it's amazing what one teacher can do. Nor would Steve have had to endure 5 years of my obsessing over the moon and MG Suite. But like any good advisor, Steve was always quick to set wind in my sail and let me drag him to the moon. And more often than I'd like to admit, pulling me back down to earth with some of my crazy ideas. But what's really impactful to me is Steve and I's relationship quickly, developed. Steve was a great mentor for me and a champion for me early in my career and to this day. And both Russ and Steve, not long after the mentorship developed, that we become friends. So thank you. It was a really exciting time to be at Brown University as a lunar petrologist. My dissertation committee was built with an ensemble cast. And so it was fantastic. I got to learn experimental petrology from Steve and also Mac Rutherford and his, legacy in lunar science. But then we were also placing our results into the regional or even global geologic context with Carly Peters and remote sensing observations. And then, of course, with Jim, I remained process driven and able to take what we can learn on one planet
and maybe go somewhere else and learn something new based on that. And through the comparative planetology perspective, thinking about each planet sort of being its own sort of unique experimental constraints. So thank you to those guys in my dissertation committee, but Brown was filled with many great teachers: Reed Cooper, Yan Liang, Alberto Saul, and of course Paul Hess. And friendships can make any place feel like home. And so I was very fortunate again to have a great cohort of grad students to learn alongside of, and so although I don't have pictures of everyone, these were kind of the most wholesome and least incriminating. And so you could say my research career kind of started with spinel and performing reaction experiments between MG Suite liquids and anorthite or synthetic equivalents of those, and looking at the reaction products and the spinel chemistry that forms during that reaction as a simulation to melt rock reactions on the moon. And then, of course, tying that back to some of the surface observations and remote sensing that Carly Peters and Deepak Dinger and others were finding, both the near side and the far side of the moon. And so by linking those experiments to both the Apollo collection sample return and also the orbital remote sensing database, we were able to develop a new proxy for ancient MG Suite magnetism across the surface of the moon. And this was so exciting because it had all these cascading implications. And I have this huge notebook of all these fun ideas to sort of explore. Is creep required for MG Suite petrogenesis? It looks like it's on the near side, but we see MG Suite on the far side. What type of global emplacement process puts these magmas all over the moon? Unfortunately, this is where my career kind of took a big deviation, where I had a postdoc lined up that unfortunately fell through last minute. And so I was left sprinting towards unemployment, no funding and no institutional support. And so I joke, but my first postdoc was serving margaritas and making tableside guacamole. But when faced with the choice between unemployment and employment, money is always going out, so you need money in. And so I had to take a full-time job waiting tables day and night. And if I could get someone to cover for me to not close during the lunch shift, I usually had about 2 to 2.5 hours in between the lunch and dinner shift. And so I would sprint across the street, go to the coffee shop, and write and research. And one of the contributions there was deciding, after I'd saved up enough tip money, I wasn't bad at waiting tables, I was able to pay out of pocket and decided to invest in myself to go to the New Views in the Moon 2 workshop. And so this is an abstract title there, and 7542 Harlan Walk was our apartment address. And that's me and our dog Declan on the floor of our apartment. Those who know me best know that I love to work on the floor. And hoodie elbow sleeves are all worn out. Anyway, this was a good idea. Anyone who has invested in themselves know you have to make it count, because that money's going towards you. And so I had a great experience at that workshop and got involved with 3 different chapters on the New Views of the Moon 2. And for me, a budding petrologist, this was absolutely a dream come true to be involved in these chapters in a project like this, because of the state at which the original New Views of the Moon was during my time in grad school, where I literally tore through it, And so I can only hope that these chapters and the others in there suffer a similar fate with the next generation. Another contribution, working and writing in between those shifts, was our study of MG Suite volcanism. And this is just based on the basic principle that kind of regardless of the range of parental melt compositions you would assume for the MG Suite, they were all much more buoyant than the Mare basalts, especially the high titanium magmas, which have clearly erupted onto the surface. And so why are all the MG Suite samples we're looking at predominantly plutonic? And so we came up with a predictive model based on this, looking at buoyancy-driven ascent and hydrostatic ascent models, to come up with a little bit of a predictive model based on the GRAIL data that had just come out on where we might find MG Suite volcanics. And that if we continued looking or continued sample return, we should see these extrusive equivalents in the sample collection. And so this has been really, really exciting to now see the next generation of scientists, going back and revisiting the Apollo collection, seeing the ANCSA initiative take its route in several different directions, but finding examples of what looks like very much MG Suite, but basaltic or extrusive volcanic textures. And it was a lot of fun getting to work with Amanda and Jess on the top paper there. And Chris invited me to his dissertation presentation. And this is really meaningful to me, not because they're citing our work or our study, but because they're referencing kind of this moment in my life where I didn't know what was going to happen. And I got really good at making guacamole. And so it's very meaningful to me to see that and just be involved and watch it happen and unfold. Thankfully, you know, after some 54 rejections later or something, I have the list. I have 3 individuals I want to thank, though, that were a turning point for me to help kind of get me back on track and could see that I was fighting, wanting to stay in the science community, and gave me a shot. So the first is Juliana Gross. I got to start working with Juliana at Rutgers University while she was still there, now our Artemis curation lead, thankfully. But she was awesome. I got to learn a lot about meteorite analysis and also kind of the synthesis of expanding the Apollo collection with the lunar meteorites and what we can learn about that and defining creep-free versus creep-bearing differentiation trends of MG Suite. The next 2, I'd like to thank Louise Proctor and Dave Draper, who gave me a shot, selected me for the inaugural Gordon McKay postdoctoral fellowship, jointly between the LPI and NASA Johnson Space Center. And ultimately, these opportunities, though they were on the precipice of COVID, gave me essentially ultimately led to my taking the oath of office and joining the NASA family. And this was an opportunity of a lifetime for someone like me. I grew up in a small town, South Dakota, and growing up, I didn't even know enough to dream of something so big. And this is a picture, a moment, a impromptu moment. I was called into a meeting one morning, had no idea, but it sounded serious because it wasn't on my calendar. And about 20 minutes in walks Bert Laws, director of the Exploration Architecture Integration Science, and chief scientist Eileen Stansbury, presenting me with the award for the work we did on mantle overturn. And that was a huge surprise, but I can't tell you what an honor it would feel like to have that. Maybe if we have a little more time, but another big shout out to all the people at NASA, my NASA family, I feel, XPET, XI3, XI2, XI4. But in particular, I want to give a shout out to Justin Filiberto and Liz Rampy, who were both acted as my direct supervisors at the time. And I felt an immediate and an intentional and a genuine passion for my career development from both of them. And it was hugely important to me. Recently, I've gotten involved with the Lunar Exploration Analysis Group, and this has been a really fun learning experience for me and such a wonderful team of people that are all dedicated to doing the kind of the same thing and making lunar science present and accessible to the community. But I do want to highlight both Amy Fagan and Tim Glotch, who behind the scenes have really helped me transition back into academia and navigate kind of my unique pathway through my career. They've been instrumental. Thank you. Lastly, my favorite rocks, my family, my wife Kelsey and our son Parker were there through the thick and the thin and supporting me all the way. And of course, our dog Declan there too. And so I just thank everyone again and helping me stay in the fight.
So wonderful talk, Tab, and two things that I took out of that. Number one, I really want your guacamole recipe. I'm serious. It's a life skill, I think of it, you know. So and then what you said about amazing what a teacher can do. And we've seen this thread with so many people about one person that's changed a life. And this is one of the reasons that we've spent so much effort, and I'm looking right at my friend Brian Day here, engaging with teachers because they can make that difference. You know, one conversation makes a difference. I've had those conversations that have changed my career path as well. So I really wanted to highlight that, and thank goodness for Russ, because you know, and we should thank him because he made it so that you're here right now, which is awesome. So I want to move on. Our third recipient here is Dr. Jacob Richardson. Dr. Richardson is a planetary geologist at NASA Goddard Space Flight Center, and he's known for his work on lunar volcanism, geophysics, and analog field studies. I've been in the field with him a few times. With over 15 years of research experience, Jacob uses geophysical methods, orbital data, and field campaigns to investigate planetary volcanoes and the deep interiors of the moon and other worlds. Jacob serves as the deputy PI of the Survey Geodes team and is a member of the Artemis II lunar science team. He's been instrumental in training astronauts for future lunar missions, developing curricula on lunar geology, moonquakes, and volcanism. His leadership in NASA's GIFT and RISE 2 programs helped establish a widely adopted code of conduct and fieldwork Bill of Rights. And this is something Survey appreciates very deeply, what you've done there. He currently serves on the League Executive Committee, where he helped lead the development of a key lunar science strategy document. Dr. Richardson's dedication to science, leadership, and community makes him a standout early career scientist. So congratulations, Dr. Jacob Richardson. Okay. Take this down. Sure. No problem.
Thanks. I mean, thanks everyone. And thanks to Survey, thanks to those who thought to nominate me. For some reason, this is like a huge honor. And just like you both have said, Ariel and Tab, just to share this with you this year, I am surprised and thrilled that I get to work with both of you on like a daily or a weekly or a monthly basis. And every time I get to talk to you, it's just like the way that you both dedicate yourself to science and also dedicate yourself to community is something that I'm really proud to just be a participant alongside of you for. So thank you. And obviously thanks to Survey. I wanted to start by actually talking about Sue Niebuhr. I didn't know her well, but I did get to meet her when I was just starting out at in planetary, finding my way to conferences somehow. She didn't know who I was, but she was building a home for me, and I think that's something that I've been thinking a lot about lately. Sue Niebuhr, when I was starting out, there wasn't a lot of queer organization that was at least accessible to me when I was going to these places. And so it was actually like her work in Women in Planetary Science and those breakfasts at LPSC, if you remember those, where I felt some of my first sense of community in this new discipline I was joining. So thanks, Sue. And it wasn't just Sue, right? It was a lot of people. It was Jake Bleacher and Noah Petro, Laura Bleacher, and Sarah Noble. A lot of people were building homes for all of us as next gen folks, and I think that that's building a home is kind of what I want to talk about today. I did want to thank some folks along my journey, right? So I got my geology degree. I found out about geology too late, just like everyone else. When I went to Eastern Michigan University, and it was Professor Christine Clark who took me under her wing, gave me my first research experience, gave me my first talk opportunities, showed me flyers that she had just randomly found where if I go to pretty distant conferences, they would be free for students, and then there'd be all these nerds there talking about planets for some reason, and I had said I was interested in that, so as long as I could pay for gas down to Houston, I could get there, and so I'm here, so thanks to Christine. And then Dr. Jake Bleacher probably grabbed a flight, but he gave me my first job at NASA. He told me to look at volcanoes on Mars, and that was addicting. He took a chance on me. The thing is that he told me once that he had a big stack of resumes from undergrads, and he picked mine out of that. I didn't come from the highest ranked university. I did not have the best grades. In a meritocracy, there's no reason for me to be on this stage today. And it's only because of Jake Bleacher taking a chance on me for some reason that I'm here. And then, of course, more chances were taken. Chuck Connor gave me my job at University of South Florida in his lab looking at monogenetic volcanoes and all across the world and also in space. And so thanks to him, I'm also here. At the end of grad school in Tampa, I didn't think I'd like Tampa. I did get a husband out of it, so that was pretty nice. And some papers, so that was great too. And so I also wanted to thank my husband, Miles. I wrote here, he reminds me to eat, which I think is the most important reason. So that also helps me still here. And then of course now somehow I'm still here thanks to Geodes, and Nick Schmer and I started working together to think about how can we bring the next generation of geophysics to the moon. And I think that thanks Nick. Of course it's not just those folks, but also that I wanted to thank way more people. I don't really have time for it, but I wanted to say, by way of maybe advice to anybody early career in the audience, that you should be ready to steal things from your mentors and your role models. I think that everything I have professionally is due to me just outright stealing the best practices that I've seen from my role models. When I am in the field and I have to make a quick decision, I stop and I think, how would Patrick Welly work towards this? How would he approach this problem? When I think of how do I dedicate myself better in service of a mission, I stop and I think of what would Dr. Kelsey Young do in this situation. And then I'm honored to have so many more. I wrote I made one slide here of a bunch of people. Let's see if I have to click it again. This is like just some people I thought of. I thought of a lot more, but they wouldn't fit on this slide, so I'm sorry. But these are a lot of my role models. When I see their faces, when I think of what their contribution to science is, I think of really specific lessons that they've taught me. So instead of putting their names out here, I put what I think about when I think of them. And I just wanted to thank so many people who have just like what everyone's been saying. We are here because of the people who have built a home for us. So I think that now would be the time when I was expecting to kind of talk about, field research or lunar volcanism or something. But I thought instead, I'm at Goddard Space Flight Center in some really weird weeks, and I thought I might bring to the podium here what we've all been talking about in the halls, that we're here in a hard time. I don't know how to really talk about that, so it's going to be awkward. But but I think a lot of people here understand that, everybody in this room is going through a hard time right now. At Goddard, a lot of people are leaving. I think at NASA, a lot of people are leaving. I expect most people know this. I think between now and a month from now, 3/4 of my chain of command that will no longer work at NASA. And to be honest, I don't blame them, and I don't judge them for leaving. And in a way, I feel honored sometimes, because I know that the reason why so many of my mentors and my role models and my bosses and my colleagues at NASA are leaving is because they have the understanding or the hope that by them leaving, we can stay. So I thought that for the rest of my time, I'd like to talk about what it means to stay. And have I ever thought about quitting? I think not recently, but to be frank, I'm a gay field geologist. I have always thought about quitting. I've always wondered if this is the right place for me to be. I think that there's literature to back it up. You can read I think Olson et al. 2018 paper, probably in EOS, where it's queer geologists, and not just queer geologists, understand that at some point they have to make a decision. Do I go out into the field? Do I not? Is geology right for me? Because being in remote places sometimes brings on an increased risk. And that's always been a persistent question. Is this the right career for me? Is this a safe career for me? And that's one of the reasons why I joined with Nikki Welly, Patrick Welly, Kayla Berry, to start making field work safer for at least my team. And ever since then, I haven't thought about quitting. And so thank you. But what does it mean to stay? I thought I've also been thinking a lot about history over the last couple of months, especially in these times, and I've been thinking about the history that we share in our discipline. I have been thinking about Galileo, and I thought maybe we should think about Galileo today together. Everyone knows Galileo's story. He was placed under house arrest for his life for saying things like, Venus has phases, Jupiter has moons. When I look through a telescope at the moon, it has craters. And he didn't know how to deal with some of his colleagues. He wrote to Johannes Kepler and said, how can I talk or convince my faculty? I don't speak Italian, so I'm ruining this. But how do I convince my faculty to anything when they won't ever consent to simply look through the telescope at the moon or the planets or the stars? His government essentially told him that what he was doing was part of a grand political hoax designed to tear down society as we know it. Obviously, he didn't see it that way. But under such pressure, why would he stay in science? Why would any of us stay in science under something like that? I've also been thinking of maybe somebody slightly less known, maybe some people know, Asaph Hall. Asaph Hall was a guy who got his job in Washington, D.C. As an astronomer for the Naval Observatory in the early 1860s. The early 1860s was an awful time to be in Washington, D.C. His day job was to look at Mars through the telescope, and his time off when he wasn't working was taking day trips to fresh battlefields looking for the bodies of his friends. It was a rough time. Why? He wrote to his wife that he could hear cannon fire from his telescope in the daytime. I don't know what made him persist. I don't know why he would choose to be a scientist when there are obviously bigger problems to solve than anything looking at Mars or Mars related. Obviously, I think we can all attest to that. But I think for both of these figures, we can think of their legacies. I don't know if this is why they stayed, but obviously, Asaph Hall's legacy, 12 years after the Civil War, he looked up one night and he saw Deimos. The next night, he saw Phobos. people in this room get to study those moons today. Galileo's legacy doesn't really need to be talked about in this room. We don't have to talk about the literal spacecraft with his literal name that went to Jupiter. We don't have to talk about David Scott's science demonstration on Apollo 15, dropping the hammer and the feather. But I thought what I might bring to this room is something that I think is a much more important legacy. 10 years after Galileo died, his students were inspired by the way he approached science. And he essentially single-handedly invented this idea of an experiment, the experiment. They made a new society, a new academy that only lasted 10 years, but they made an academy dedicated to the idea of the experiment as a way to do science. And in those 10 years, we as humanity got the foundations of the Enlightenment 100 years prior. We got a revolution in reproductive theory. We got, for some of us in this room, probably care about thermal convection. If you're not a thermal convection girly, you might care about the most important thing we got from that, which was Steno's laws. In those 10 years, we got superposition and cross-cutting relationships, things that we use today at this conference to investigate the moon. I think that, I think I've probably spoken for too long, but I think that we can think about what these legacies mean for how we should act as we stay. I think that the first thing, when I think of Asaph Hall, I think that our duty is to help. Something that was shocking to me was that he didn't stay in his office. When he heard the cannon fire in the daytime, he went and he helped. He helped his friends, his family, his community. He went and did his duty on the battlefield, even if he wasn't fighting the war. And I think it's our duty to help when we hear the cannon fire from our offices. I think that when, Galileo, I think it's important for us to remember that it's our duty to speak the truth. And it's our duty when our institutions are told not to broadcast our results, that our results might not be what we need to hear right now. If we believe in our results, it becomes our duty to share those. And then I think most importantly, and part of, I think in the spirit of this award, I think it's time now, of course, I think everyone's saying this in the halls, I just want to say it up here on the podium, that now it's time to make sure that we have built a resilient next generation. I think that now is, a time that the people in this room, the people listening online, people who have been here at this conference need to continue this even in the wake of the uncertainty. Ariel talked about how programs have already been cut. I think Survey is delayed, but we don't know the future about anything right now. But if we take our eye off of this grand prize of what is the legacy that we're trying to build if there's nobody next to carry it on, I think that that's our main mission, is building that resilient next generation. That's something that I've loved about Survey. Survey every day, and I've seen it all this week, is building homes for people that we don't know yet. And I think that that's the strength of our community. And our community, whatever it looks like, I understand there's a lot of uncertainty. This room might look very different next year. But I think it's just so important that we do this, that each one of us has to take on this duty. We have to continue to make opportunities throughout this uncertainty. We have to take chances on the passionate early career scientists, even if their CVs, don't match those, don't match, the meritocracy quite yet. And I think that most importantly, we have to continue, whether our institutions are telling us to avoid this or not, we have to look far and wide outside of our normal bubbles for the best and the brightest. They're out there, even if they haven't found their pathway to NESF yet. And I think that, this is the legacy that I think Galileo successfully built. This is the legacy that Sue Niebuhr successfully built. And I think that this is the legacy that I hope we all, partake with. So thank you so much, Greg.
I'm not sure how much I can say after that. Wow. A couple of things I did want to mention. I neglected to mention how Jacob was one of the key leaders in our EDIA focus group for survey, and that was, to me, other than our science, we were already doing just fine at our science. That was, to me, our highest institute priority. And for me, on either January 20th or 21st, it was like a knife in the heart when we had to stop those activities. I decided to devote the rest of my life to it, to help, yourself and others. And I also didn't know the story about, I knew you had talked about safety, but I didn't know in the field, but I didn't know the motivation, and that's wonderful, because we have a gay daughter, and we are very sensitive to that kind of thing for her safety as well. And all I can say is I'm glad Jake Bleacher took that chance, because we are all benefiting. Thanks so much, and congratulations to all of our NEBR award winners. What a bright future we have ahead, right? And where these three are, there's a whole lot of others as well, and I have every confidence you guys are going to create a great future for all of us. So thank you. Lunchtime.